All right. All right, we're going to go through some definitions first, and we'll do gas laws, and then we will get into the basic refrigeration cycle, and we'll see how that all relates. I know the modules 1 and 2 are tough, a lot of the formulas, a lot of talk about how many BTUs does it take to take a 10-pound block of ice at minus 10 degrees and make it into 250 degrees steam, but that's all for purpose. We'll kind of get into that in just a bit. Okay, first definition, heat. Now, when you think of heat as a human being, that's like your stove and it's hot and you burn, but truly heat is just a form of energy.
Yun. Abante mo.
Molecules in motion. So even with an ice cube that's at 32 degrees, there are molecules in that ice that are moving, and there's still heat there. It isn't until you get down to minus 460 degrees that all molecular motion stops. And that's never been reached yet. It got pretty close to that. So I want you to start thinking of heat as molecules in motion, not so much as something that is hot to your touch. And heat always flows from a substance that has more heat or more molecules and motions to one with less heat. This will give you a quick example right here. For example, this block of ice at 32 degrees does have molecules in motion, but they're pretty much bonded together, and they're not moving very much. They're just sitting here pretty, while they are moving, they are not bouncing into each other too much, or more or less bound together. That's why that gives ice its solid form. And as we start to add heat to the ice and it begins to melt, the molecules begin to move a little bit faster. So not only are they bound together, they start to cut loose their binds with each other and turn into a liquid, and they start to exert some force in downwards and outwards direction, like in this container. Then as we add more heat and we turn this water and liquid into vapor, those molecules are bouncing around really fast, and it exerts some pressure in all directions. And that's the one thing you need to remember when we're talking about pressure. That's where you get pressure. This example here that shows that blows a cork off the bottom. You get so much energy and pressure in here that in the form of heat. Okay, heat flow. When I talked about heat earlier, it's molecules in motion. So this makes sense to us. If we have 100-degree Fahrenheit block of lead here and set it next to a system.
Okay. Ganyan yung heat flow. Yung heat, dito 100 degrees Fahrenheit. So paano yung takbo heat flow? Ang heat flow, kung saan malamig, doon pupunta ang init. natural na takbo ng init yan. Hindi yan pwedeng magpunta sa mas mainit sa kanya. Hindi yan gano'n. Ang heat, nagpupunta yan kung saan siya malamig.
75-degree Fahrenheit block of lead. Of course, we recognize that the heat will flow from the substance with more heat or molecules in motion to one with less. But now we don't usually think of minus 200-degree Fahrenheit and minus 350-degree Fahrenheit as having heat, but it still does. It has molecules in motion, although not as much as these blocks up here. There is heat energy contained in this block of lead, and the molecular motion or heat energy will in fact flow from a substance that is minus 200 degrees to minus 350 degrees Fahrenheit. And that's why I want you to think about heat again as molecules in motion, not something that is hot or cold to our touch. All right, in air conditioning, we have two forms of heat, types of heat that we like to talk about. One is sensible heat, and that is where if you add heat or molecules or heat energy in molecules of motion to a substance, it changes the temperature that you can measure with a thermometer. And then we have latent heat, and that latent means hidden, and that heat that cannot be measured by a thermometer. And what it does is, at a certain point, and we use water in the example in the textbook, when you start with a 75-degree can of water and put it on the 500-degree stove, it starts to increase the temperature. And if you have a thermometer in there, it's going to show that temperature increase. That's the sensible heat. At a certain point, if you're at sea level, it's 212 degrees, the water begins to boil, and that's changing of state from a liquid to vapor. And it remains steady at 212 degrees and will not, that water does not increase temperature because all of that heat energy that's being absorbed is changing the state of the water from liquid to vapor. That's called latent heat because even though you're adding heat, you can't measure it with your thermometer. Okay, saturation. And we'll talk about water first, then we're going to talk about refrigerants because they're very similar in their properties. The saturation is when a substance is in the form of both liquid and vapor, and if heat is added, it'll begin to change state into vapor. And if heat is removed, it will change state back into liquid. So the definition of saturation is when a substance is in the form of both liquid and vapor. When we add heat, it changes state, begins to change state into vapor. beaker of water here, and you're adding heat to it, and it's boiling, and you put your finger in there and you get burned. But when we talk about refrigerants, they boil at much lower temperatures, so we're gonna erase boiling from our vocabulary, and changing state is what we're going to talk about from here on out. All right, so here is the diagram from our textbook, and it starts out at the bottom of the graph with 0-degree ice. We're not going to worry much about this 0-degree ice until we hit 32-degree water at this point right here. Let's talk about this water. We have that water on the stove like we talked about earlier, and as it is heated up on the stove, the temperature begins to rise. At this point, we're at 100 degrees over here. Now, as that heat that is being added raises the temperature, that is the sensible heat. Remember, sensible heat is